Section. Introduction. We're going to talk about the recent progress in natural language processing, which has been largely driven by large pre-trained language models like GPT-3 and 4, Palm and Gemini, and many others. However, we can't overlook the importance of open access language models such as Llama 1 and 2, Falcon, Bloom, Opt, or Neox, Pythia. These models are freely available for researchers to use and modify, which wouldn't be possible with proprietary APIs. Despite their availability, these models are challenging to use due to their enormous size. They require multiple high-end GPUs even for basic tasks. To use these models on more affordable hardware, we need to either compress the model parameters or offload them to cheaper storage options like RAM or SSD. Some recent works have introduced sparse mixture of experts (MO) blocks to modify the transformer architecture. These MO blocks contain multiple layers, or experts, and a gating function that decides which experts to use for a given input. This allows for more efficient training as only a small portion of all experts are used for any single forward pass. MOs are among the largest and best available language models. However, many techniques for efficient language model inference were not designed with MO in mind and perform suboptimally on modern large language models that use MO layers. In this work, we aim to develop techniques for running large MO language models with limited GPU memory. Our main goal is to generate tokens with Mixtral -8x7b instruct, a MO-based chat assistant, on desktop-grade hardware where only a fraction of experts fit into the accelerator memory. We've observed how MO language model accesses its experts between tokens and found some patterns. Some experts are reused between adjacent tokens, and the model hidden states of early layers already know which experts are to be used at subsequent layers. Based on these observations, we've designed a MO-specific offloading strategy that significantly reduces GPU-RAM communication, leading to faster generation. It also guesses which experts are needed ahead of time to better overlap expert loading with computation. We've also considered the specific scenario of running Mixtral -8x7b instruct on AT4, RTX 3060, and RTX 3030 mobile and developed a practical combination of mixed quantization and the proposed offloading algorithm to run this model interactively at 2 to 3 tokens per second depending on the hardware. The recent surge in MO language models builds on an old idea of training ensembles of specialized models, experts, and a gating function to select the right expert for the task. To achieve specialization, MOs learn by simultaneously training the gating function to choose the best experts and training the experts themselves on samples assigned to them by the gating function. Since then, many different MO variants have emerged, including mixtures of SVM models, Dirichlet processes, and various neural networks. The full model consists of a recurrent neural network backbone and a MO module with up to 131,072 experts. When processing a given token, a linear gating function selects the 4 most suitable experts based on the latest hidden state. The model is trained end-to-end to minimize cross-entropy, with an additional regularizer to promote equal expert utilization. MO models not only improve perplexity but also learn interpretable expert specializations. For example, some experts specialize in prepositions, while others learn to express a particular concept like speed. Several lines of work explore MO with transformer-based language models for machine translation, masked language modeling, general-purpose LLMs, and others. Most of these models follow traditional, dense, transformer architecture for embeddings and attention layers, and only use mixture for the feedforward, MLP, blocks and use a linear token-level gating function. A common observation across most of these works is that MO models are cheaper to train and inference, but require more parameters than a dense model with equivalent perplexity. Pre-trained mixture of experts LLMs have been openly available for over a year. However, these models seem to have gained less traction than equivalent dense models, arguably because their sheer model size, over 1 trillion parameters, makes them difficult to use. Most recently, Mistral AI released a family of sparse mixture of experts models called Mixtral -8x7b with near state-of-the-art performance. This model has already inspired several follow-up works and practical applications, but it still requires a high-end GPU accelerator. Section summary. Many recent advances in natural language processing rely on large pre-trained language models, but the use of open access models allows researchers to modify them locally, which is not possible with proprietary APIs. However, these open access models are difficult to use due to their large size, requiring multiple high-end GPUs. In this work, the authors developed techniques for running large mixture of experts language models with limited GPU memory, specifically focusing on the inference of MIXTRAL8X7B Instruct, a MO-based chat assistant, on desktop-grade hardware. They propose a MO-specific offloading strategy that reduces GPU RAM communication and guess which experts are needed ahead of time, achieving interactive token generation on affordable hardware. Section: Post-training quantization of LLMs. We're going to discuss how to make large language models, LLMs, more efficient. One way to do this is by reducing the model size through techniques like quantization, sparsification, or factorization. These aren't unique to LLMs and have been used in other fields as well. However, when it comes to large transformer-based language models, quantization presents some unique challenges due to the presence of outliers. Generally, the best compression rate for most LLMs is 4 bits per parameter. There are more aggressive algorithms that can compress to 3 or even 2 bits, but these usually don't perform as well as simply choosing a smaller model and quantizing it to around 4 bits. Recently, there have been several works on quantizing mixture of experts models. Another approach to handling large models with limited accelerator memory is to offload their parameters to another, cheaper memory, like system RAM or even an SSD. This technique works by loading model parameters just when they're needed for computation. Since most deep learning models use layers in a fixed order, offloading can pre-dispatch the next layer parameters in the background, ahead of time. This works particularly well when processing large batches of data, during training or large batch non-interactive inference, where each layer processes a lot of tokens each time the layer is loaded from RAM. However, for interactive inference, like chat assistants, offloading works significantly slower than on-device inference. This is because interactive inference generates tokens one at a time, from left to right, and therefore spends most of the time waiting for the next layer's parameters to be loaded. Our analysis isn't specific to any hardware setup, but we're targeting the hardware specifications of inexpensive or free-tier cloud instances and the upper half of gaming computers. These typically have enough system memory to hold model parameters, a GPU with 11 to 16 GB VRAM, and host-to-device communication at 8 to 16 GB per second. If we look at popular open-access mixture of experts models, we find that all non-experts can fit a fraction of available GPU memory. However, the experts that make up the majority of model parameters don't fit even with quantization. And even if we could fit the model parameters in memory, running generative inference requires additional memory for layer activations and past attention keys and values. In this work, we're trying to find the best way to run modern mixture of experts LLMs on desktop or low-end cloud instances. Specifically, we're focusing on generating tokens interactively, i.e., generating multiple tokens per second at batch size 1. The generative inference workload consists of 2 phases: 1. Encoding the input prompt, and 2. Generating tokens based on that prompt. The key difference between these 2 phases is that prompt tokens are encoded in parallel, whereas the generation runs sequentially. In general, phase 1 works relatively well with existing mixture of experts algorithms, since each layer can only be loaded once for the entire prompt. However, when generating tokens, one must load the layer once per each token generated. In practice, this means that inference speed is limited by how fast one can fetch parameters from system memory. We've noticed some patterns in how the mixture of experts model loads its experts, and we're proposing ways to exploit these patterns to speed up inference time. Mixture of experts language models often assign individual experts to distinct subtasks. However, this doesn't mean that the model uses the same expert over long stretches of tokens. Some experts are active in short sequences of 2 to 4 tokens, while others are often used with gaps. To take advantage of this pattern, we can keep active experts in GPU memory as a cache for future tokens. If the same experts are activated again in the future, they will be available instantly. Naturally, the number of experts that can be stored this way is very limited by the available GPU memory. For simplicity, we choose to always keep a certain number of least recently used experts as a type of cache. If this number is greater than the number of active experts, the cache will save experts from multiple previous tokens. For simplicity, we keep the same number of cached experts for each mixture of experts layer. We've found that even this simple strategy can significantly speed up inference for modern mixture of experts models. Section summary. the section discusses the challenges of quantizing large transformer-based language models, LLMs, and the technique of offloading model parameters to cheaper memory for inference. It also introduces the concept of expert locality and LRU caching as a strategy to speed up inference for mixture of experts LLMs. The authors aim to optimize the inference process for generating tokens interactively on low-end hardware setups. Section: Speculative Expert Loading. We're going to discuss a concept called speculative expert loading. In simple terms, this is a method to speed up the process of loading experts in a mixture of experts model. You see, while least recently used, LRU caching can help reduce the average time it takes to load an expert. Most of the time spent during inference is still waiting for the next expert to load. This is because, unlike with dense models, offloading can't effectively overlap the loading of experts with computation. To understand this, let's break down the process of generating a single token in a model. It starts by embedding the previous token, then alternates between running self-attention and a multilayer perceptron, MLP, for each transformer block in the model. The outputs from the last transformer block are then used to predict the next token. In regular models, this architecture allows for an efficient offloading schedule that preloads the next transformer layer while the previous layer is still running. However, this isn't possible for models, where the MLP layers choose which experts to load just before computation. This is because the system can't prefetch the next layer until it knows which experts should be loaded. Modern language models choose active experts using the final outputs of the previous layer, which means they can't be prefetched in parallel with the previous layer. While it's not possible to reliably prefetch the next set of experts ahead of time, the system could still try to guess the likely next experts and load them speculatively, while processing the previous layer. If the guess is correct, it will speed up the next layer inference. If not, it can load the actual next layer's experts later. This type of speculative loading doesn't change the final model predictions, but may reduce latency if the guess is accurate enough. We found that it's possible to get an accurate guess of the next layer's experts by applying the next layer's gating function to the previous layer's hidden states. This is because transformer layers are residual, meaning each layer adds to the previous hidden states instead of recomputing them from scratch. Now, let's talk about the practical design considerations and implementation details that we used for inferencing language models on consumer and low-end cloud hardware. Our system design combines caching and prefetching techniques and a mixed quantization scheme. As we mentioned earlier, there are multiple weight quantization algorithms optimized for large language models, LLMs. Model compression has a natural synergy with offloading because compressed models take less time to load onto a GPU. In our experiments, we also observed that models get better quality size trade-offs when quantizing experts to a lower bit width, while keeping all non-expert layers at 4-bit. We use half-quadratic quantization, HQQ, a data-free quantization algorithm that supports a variety of bit rates. We also tried the sub-1-bit quantization from QMO that worked well on the Switch C2048 model. However, we found that sub-1-bit compression caused too significant a loss in perplexity for MIXTRAL8X7B models. As for expert offloading, we use LRU cache with an equal number of cached experts per layer. For MIXTRAL8X7B, we use 2 for 12 GB GPS and 4 for 16 GB ones. We trigger speculative expert loading immediately after the system finished loading all experts for the current layer. The speculative expert loading fetches 1 to 2 most likely experts. The newly loaded experts do not replace the currently cached experts. If a speculatively loaded expert was later used during next layer inference, it will replace the least recently used expert from the next layer's cache. Many consumer devices and free-tier cloud instances have limited host RAM that cannot fit the entire model. In these cases, the experts must be split between host and device memory. To support this, our implementation of expert LRU cache splits experts between host and GPU devices. When loading an expert to the GPU cache, the system also offloads the least recently used on-device expert back to RAM so as to preserve memory parity. To speed up offloading in practice, we allocate all expert parameters in a contiguous memory buffer that can be moved as a single host to device copy. For host-side RAM experts, we pin this memory buffer for faster communication. Our implementation additionally allocates 4 on-device buffers used to copy and prefetch experts asynchronously, without modifying existing experts. These buffers are shared between all Mo layers to reduce memory footprint. Overall, the system requires a number of expert memory buffers split between host and device memory and 4 temporary buffers, the size of each buffer being equal to a single expert. Section Summary. In mixture of experts, Mo, models, the time spent waiting for expert loading is a major bottleneck. Unlike dense models, Mo offloading cannot overlap expert loading with computation, resulting in inefficient inference. To address this, speculative expert loading can be used to guess and load likely next experts while processing the previous layer, reducing latency if the guess is accurate. Additionally, practical design considerations such as caching, prefetching, and expert quantization can be implemented to optimize the inference process on consumer and low-end cloud hardware. Section: Experiments. In this section, we'll be testing our earlier assumptions about the behavior of mixture of experts, Mo, models, and comparing the speed of inference under different conditions. We'll be focusing on the Mixtral -8x7b and Mixtral -8x7b instruct models, as they are currently the most advanced open-access Mo models available. We'll start by examining the effectiveness of expert caching and preloading separately. Then, we'll compare different model compression algorithms and confirm our earlier hypotheses. Lastly, we'll measure the speed of inference in various hardware setups. In our first test, we'll be looking at 2 strategies for offloading experts, least recently used, LRU, caching and speculative loading. We'll be using the Mixtral -8x7b instruct model on the Open Assistant dataset for this. We'll measure the expert recall, which is how often an expert needed for inference was already available on the GPU. We'll test LRU caching by running the model on recorded conversations and measuring the recall for different cache sizes. Then, we'll test speculative loading by guessing which experts should be loaded next and measuring how often we're correct. A recall of 1.0 means that both active experts were pre-fetched. We'll test speculative loading in 3 settings, 1, 2, and 10 layers ahead. Next, we'll test how different quantization schemes affect Mo performance and size. We'll be using the Mixtral-8x7b model again, but this time, we'll use a non-instruction tuned variant. We'll measure Wikitext2 perplexity and 5-shot MMLU accuracy. Our goal is to find the best balance between size and performance for offloading with the target setups. We'll be using the HQQ data-free quantization algorithm and considering the following quantization schemes: FP16, no quantization; HQQ 4-bit with group size 64, scale group size 256, HQQ 3-bit with group size 64, scale group size 128, and HQQ 2-bit with group size 16, scale group size 128. We found that it's beneficial to quantize experts to 3 or 2 bits while keeping attention layers to a higher bit width, 16 or 4 bits. Based on these evaluations, we chose 2 quantization schemes that offer favorable performance size trade-offs within the target hardware constraints. Finally, we'll evaluate the performance of the Mixtral-8x7b instruct model using the offloading techniques proposed in this report. We'll be generating tokens via sampling on Open Assistant conversations and measuring the average number of tokens generated per second with batch size 1. We'll consider 4 hardware configurations: a free-tier Colab instance with AT4 GPU, a past-generation gaming laptop with RTX 3080 mobile, a mid-range gaming desktop with RTX 3060, and a high-end data center server with a 100-80 GB SXM. We found that all evaluated setups can generate 2 to 4 tokens per second with the full algorithm. Using preloading appears to be most beneficial on RTX 3060, possibly due to lower LRU cache size. Interestingly, RTX 3060 desktop performs nearly equally with a much higher-end 3080 mobile. We attribute this to the fact that both GPUs are still bottlenecked by host-to-device bandwidth, limited by the PCIe architecture. Finally, all schemes significantly outperform naive offloading that loads the entire Mo layer.